Okay, I'll get started. Good evening, everyone, and good afternoon and morning for those who are joining us from abroad. It is a pleasure to invite you all to the first online meeting of Geophysical Flows Lab, which is a recently approved research initiative at IIT Madras as part of its Institute of Eminence framework. The aim of this research initiative is to establish a national center of excellence with a unified approach towards geophysical flows. It comprises 11 different faculty members from IIT Madras, who span a range of expertise, including fluid dynamics, oceanography, and aerospace engineering. We are also delighted to have the participation of Professor Debashish Sengupta from the Indian Institute of Science. Also part of this research initiative are 5 different national labs, namely National Institute of Ocean Technology and National Center for Coastal Research in Chennai, the Indian National Center for Ocean Information Services in Hyderabad, the Space Applications Center in Ahmedabad, and the National Center for Medium Range Weather Forecasting in Noida. So I'll provide a brief motivation for a minute before I hand it over to Professor Bhaskar Ramamurthy. The motivation comes from wanting to establish a unified approach. So geophysical flows are typically looked at from the perspective of field measurements, large-scale climate models, or fundamental studies of small-scale processes. But given the expertise we have assembled here for this initiative, we would like to have a unified approach because these different aspects are interlinked anyway. And the applications of this initiative includes climate and weather prediction and monitoring and understanding the ocean environment. And there is also a significant technology aspect to this initiative, which is the development of unmanned aerial systems for oceanography and meteorology. This initiative will also significantly strengthen ongoing collaborations with various international collaborators, and this also provides a formal structure for these collaborations. The international partners include ENS Lyon and École Centrale in France, the University of Washington at Seattle, the University of Massachusetts at Dartmouth, the University of California at San Diego, the Oregon State University, the University of Colorado at Boulder, Harvard University, Arizona State University, and the Woods Hole Oceanographic Institution. So in the longer run, while right now the academic participation is predominantly from IIT Madras, in the longer run, the plan is to make it a pan-India center of excellence for geophysical flows, along with the participation from the national labs that are already part of our center. So at this point, I would like to hand it over to Professor Bhaskar Ramamurthy, Director of IIT Madras, to say a few words on his vision for this research initiative. Thank you.
Thank you, Mani. Can you hear me?
Yes.
Yeah. So good evening, good morning to all those assembled here for this first meeting. I'm indeed very pleased to see this very bold effort. I say bold because for IIT Madras, we don't have really a department of geosciences or earth sciences. But when we initiated these, call for new research initiatives with the funding that we received when we were declared an Institute of Eminence by the government, I sort of knew, could guess some of the initiatives, the proposals that would come, but I never guessed that we would get something in this area. So I'm very glad to see faculty from several departments, ranging from aerospace to people in fluid mechanics, who of course themselves are in many departments, and all get together, and also more importantly get together with key collaborators in the national labs in India as well as various universities, mostly in the US, as I can see. It's a very interesting area. I don't claim to know anything about it, so I don't want to say anything about it, but it looks very interesting. And I'm very glad that IIT Madras is getting into this kind of work, which has not been our one of our areas in which we are seriously represented. And obviously, for us to do this well and hit the ground running, collaboration is the key. And I'm very glad to see the kind of far-ranging collaborations that have been initiated with institutions across the world. I would presume, Mani, that Australian collaborators would also be potentially key in this, because this is all about the Indian Ocean. So anyway,
absolutely.
So you can look at our partner universities in Australia also as a potential source.
Sure.
Yeah. The other thing that I noticed, and again, this may be something that is sort of implicit in what's written here in this one slide, is that I presume that data science techniques will also play a role in this kind of work. So we do have a large effort in data science in the institute, and and so there are people who are like, there is an effort that Balaji and others are looking at, which is more thermal oriented, radiation from the earth and so on. But I'm sure some of that interacts with the geophysical flows also. So, and some of them are working with the data science group. So anyway, I think these things will quickly expand. So, really looks exciting, and wish you all the best. I don't want to say too much more. I'm just happy to have been invited to share my few thoughts, and really wish this effort great success as quickly as possible. So thank you very much.
Thank you very much, sir. And thank you very much for this support for this initiative. We also look forward to working on it. So if you are fine, I will proceed with the presentation.
Please go ahead. And you'll have to let me leave shortly. Yeah.
Sure. Thank you very much. Okay, so I will provide a brief 10-minute summary on this research initiative before we go over to the formal talks as reflected in the schedule. So in the interest of time, instead of having everyone introduce themselves, I have provided a very brief summary of the various participants. At IIT Madras, we have Anubhav Roy in Applied Mechanics and Balaji Srinivasan in Mechanical Engineering. Bharat Govindarajan, T. Jayachandran, Joel George, Louis Tau, HSN Murthy, M. Ramakrishna, P. A. Ramakrishna, and A. Samin all belong to aerospace engineering. And we also have the participation involvement of Debashish Sengupta from the Indian Institute of Science, along with the 5 national laboratories that I just highlighted. It's quickly to recall NIOT and NCCR from Chennai, INCOIS in Hyderabad, the ISRO lab called SAC in Ahmedabad, and NCMRWF at Noida. We are very happy to have strengthened ongoing collaborations with several international collaborators. We have Amit Tandon from the University of Massachusetts at Dartmouth, Emily Schroer, Jonathan Nash, and Simon D. Zoke from the Oregon State University. Emily Schroer very recently has moved to the Office of Naval Research. Craig Lee and Eric Dazzaro from the University of Washington at Seattle. And Andrew Lucas, Jennifer McKinnon, and Sotonu Sarkar from the University of California at San Diego. We also have Amala Mahadevan and Tom Farrar joining us from Ujjol Oceanographic Institution. Andrea Maffioli, Helen Scolan, and Louis Gostio from École Centrale Lyon. Anish Subramanian from the University of Colorado at Boulder. Thierry Doxua from ENS Lyon in France. Mohammad Husam Kasaboui from Arizona State University. And Sasan Sethi from Harvard University. I will, so as I said, the main objectives of the initiative right now is to establish a center of excellence, which has a unified approach. So we would like to have each of these aspects provide input to each other. Other specific objectives include a targeted survey of coastal regions. So this involves the field measurements aspect of the initiative. As I said, a significant technology development involves the design and development of autonomous unmanned aerial systems for both measurements in the atmosphere and imaging of the sea surface. Fundamental studies that involve fine-scale processes that look at the fine-scale processes that occur in the ocean, but that are not well resolved in large-scale models is also an important part of this initiative. And finally, we have a component for coupled ocean atmosphere modeling. At the end of the day, to improve predictive capabilities, that's where we will have to invest our efforts on, or that's where we are going towards. In the first phase of the initiative, the focus of the field measurements would be in the northern Indian Ocean, specifically the Bay of Bengal, expanding towards the Arabian Sea. And as I said, but the ideas involved in this center are quite relevant for the global oceans as well. Very quickly, geophysical flow, the ocean we all know is a complex multi-scale system which has forcing and responses at very different time and spatial scales. And some of these fine scale processes are under-resolved or absolutely not resolved at all in large scale models. The presence of scales such as lateral scales such as 1 to 100 kilometers is beginning to be well recognized in the ocean now. How much they influence climate modeling and air-sea interactions is yet to be figured out. Shown here on the right top is an example of a satellite image of sea surface temperature showing very fine scales in the Bay of Bengal. And the Bay of Bengal is also a special region, not only because it influences the monsoon significantly. From a fundamental physics viewpoint, with the significant amount of freshwater input into the bay, it makes it very interesting even from a dynamical viewpoint. Shown at the bottom here is an example of a laboratory experiment modeling a fine-scale geophysical flow. So there are three different aspects to this initiative. With respect to observations, you will see more details about these in the upcoming talks. So shown on the left is the mooring observation network that is maintained by the National Institute of Ocean Technology. One of the obvious gaps you see is the lack of observations in the coastal regions. So the field observations would be focused in regions of the order of around within 300 kilometers or so from the coast, while we continue to analyze the huge amounts of data that's already been collected in the open oceans. On the right, a recent modeling study from the Indian Institute of Tropical Meteorology highlighted the importance of resolving the strong lateral gradients present in the sea surface temperature to improve the predictive capabilities of large-scale models, specifically the subseasonal variations in the rainfall in the Indian subcontinent. The unmanned aerial systems is a novel technology aspect that we would like to introduce to oceanography and meteorology. Again, there is a talk by Professor Bharat Govindarajan in this session that will go into the details of what we are developing. But very quickly, we are developing two different types of systems. On the left is a conventional quadrotor that makes vertical profiles in the atmosphere. And to achieve extended lateral horizontal range, we are also developing conventional fixed wing type unmanned aerial vehicles. The second aspect is the fine scale process modeling. Some examples of the fine scale processes that we as a group already work on are highlighted here. On the left are problems related to both the generation, instabilities, and pathways towards dissipation and mixing of internal waves. On the top is a schematic describing the importance of near-inertial internal waves in the ocean. And below, you see the importance of internal tides. We also work from very different perspectives on instabilities that occur in eddies. And shown at the right bottom is a schematic of sea spray, which is also known to be an important component in air-sea interactions. The idea of these fundamental studies is to feed back into the large-scale climate model studies and the field observations, and hopefully go towards developing parameterizations, accurate parameterizations of some of these small-scale processes to be incorporated in large-scale models. Modeling of transport and generally geophysical turbulence is also an important expertise area we have at IIT Madras. Shown here on the left top is a recent study from my group that highlighted the relevance of advective transport in understanding the patterns that you see in the sea surface temperature in the Bay of Bengal. So the various topics that would be discussed more in the upcoming talks are listed here. We are also quite interested in understanding and modeling transport of both passive scalars or fluid-like particles and inertial particles in geophysical turbulence. This is of huge significance in the transport of contaminants like microplastics and oil spill. Also very relevant for ocean biology because these are also involved in the transport of nutrients and other related quantities. Shown here is a schematic of various physical processes that could contribute to the transport of microplastics in the ocean. Several of these processes would be studied as a part of this initiative. I would also like to highlight there is an experimental component to this initiative. At IIT Madras, we host two different facilities that are relevant for geophysical flows. On the left is Waves and Instabilities Laboratory, which we study stratified flows specifically related to internal waves, both in a long tank that models two-dimensional flows. And as we speak, a three-dimensional facility is being developed to look at the three-dimensional aspects of these flows. We also host a rotating flows laboratory, which Earth's background rotation could be investigated closely. And on the right is an example of geophysical turbulence that could be reproduced in the laboratory, a model of a large-scale jet in the Earth's atmosphere or the ocean. This, as I said, there are significant societal impacts and relevance for this initiative. Improved prediction of monsoon and other subseasonal events is the grand goal of this effort. At the least, accurate parameterizations of smaller scale processes, which in turn, as we all know, significantly affects the economy of the Indian subcontinent. Ocean biology and pollutant transport is also a significant outcome of these efforts. And finally, the development of unmanned aerial systems, we believe, would be a game changer for measurements both in the atmosphere and oceanography. We'll hear more about it very soon. And these research objectives are quite relevant to a wide range of both Indian and international organizations as listed here. So I think that concludes my quick summary. I would just go over the meeting schedule for the rest of today. So we will have 3 introductory talks, 10 minutes each, and then a short 6-minute period for a discussion, followed by 7 more short talks for the rest of today. Day 2, that's tomorrow, it's organized in a similar manner, 5 short talks in each of these sessions. And the idea, thanks to input from many of you, the idea is to have a break of 4 days before the last day of the meeting. And hopefully we can have discussions in smaller groups to come up with clear roadmaps for research collaborations in the future. So the last day would be on Monday, September 13th, which would have a 1-hour-long panel discussion. I request and encourage everyone to take part. Your inputs are quite invaluable in setting the roadmap. And in the last 1 hour of day 3, we'll provide concluding remarks, which would involve on top of the roadmap that we come up with. I will also talk about many aspects of how the modalities of collaborations that could be taken up under this research initiative. And there are several other events that we have planned as a part of this initiative, which I will talk about as well, and a few other administrative details. And in the meanwhile, if there are specific questions, please feel free to email me, and I will surely take them up during the last day's discussion. And finally, as you all know, the meeting is being recorded. If you have any concerns about it, please do let me know. So if I think it's we're doing well with time, maybe without much further ado, I will request Eric Dazzaro and Craig Lee to give the first talk of the session. Thank you.
Great. Thanks, Mani. Let's see. You'll see the screen. Assuming the screen is showing up for everybody?
Yes, Craig, we are able to see the screen.
Okay, well, good evening, and thank you for inviting us here to speak of the Geophysical Flows Lab meeting. What Eric and I were tasked with was talking about observing the Indian Ocean in a fairly broad sense. And what we thought we would do is take a step back and think about why we observe the Indian Ocean, what sorts of scales that implies, what sorts of platforms, and what kinds of approaches have worked. So I'll start by talking about the why. Why do we make observations in the first place, right? What you see in this diagram, Eric and I like to think in terms of scales. And so you see these two arrows in the middle. The left-hand arrow is actually persistence and distribution. So how long do you make the measurements for? How broadly do you make them? And the right-hand arrow is resolution in time and space, where the upper part of the arrow indicates very large spans and long time scales. And the bottom of the arrow indicates shorter spans, more regional focus, very fine sampling. So why do we make these measurements? We like to make measurements for science, right? That's what we all do for a living pretty much. We think about questions of climate change. We think about gaining a better understanding of their systems for various reasons. But we also do it to support planning activities. Fundamentally, a lot of us make observations to help constrain models in some form or another, whether it's with process studies or returning data that actually goes into, is assimilated into the models, right? Constrains them and guides them. We do that largely to improve forecast capability. And we do it also to provide situational awareness at a shorter time scale, things like weather. You can think of those in very broad buckets, informing policy, very long-term decision-making, right? Infrastructure building, or environmental policy, strategy of how we plan activity on a yearly or a multi-year basis, and then tactics of local support. Weather forecasting is a good example, right, of that kind of support. And those imply different kinds of data delivery. At the policy end, we really don't care how quickly we get the data. A year or two latency is just fine. So you put a mooring out, get the data a year or two later, that's just fine. But at the tactical level, right, the data is very valuable when it comes in real time and loses value very rapidly. It has what we call a very short shelf life. So the devil of this is that the physics are nonlinear, and so there are interactions between scales. And those interactions are very, very important, right? They're absolutely critical to understanding and running some particular models that we want to be able to run. So if we think of physical processes, most of you have probably seen diagrams like this before. It's the vertical axis is temporal scales, the horizontal axis is the spatial scales. And plotted in the ovals are some baseline physical processes that we think of in the ocean. And the ovals are general in terms of their scope, but they give you a general idea of the space and time scales that these processes cover. And here we have everything from turbulent mixing down to the very smallest scales, the lower left-hand corner, to planetary waves in the upper right-hand corner, right at the longest scales, basins and years or tens of years, and everything in between, internal waves, some mesoscale processes, fronts and eddies, right? These are all things that we think are active in most ocean basins, really, some more important than others. But if we go and we plot, sorry, I'm having trouble, there we go. One of the dominant modes of variability in the Indian Ocean, the monsoon, it lands, of course, up here in the upper right-hand corner, where the mesos have scales of kind of a week, but the monsoons themselves have scales that can last beyond a year. They span the whole basin down scales of tens of kilometers, right? So that's kind of the impact we think of the monsoons. But if we think about the dynamics that govern the monsoons, right? What controls the variability in the meso, things like this, it gets more complicated. And if we think about one of the primary drivers, sea surface temperature, we can look at that, right? And realize that sea surface temperature is actually driven by most of the dynamics that we have on this plot. Most of those yellow ovals mark out a set of dynamics that have a large impact on sea surface temperature and therefore on the monsoon. So if you want to be able to study the monsoon, if you want to be able to model the monsoon, you want to be able to make observations of the monsoon, you need to be able to make observations at a very broad range of scales. So let's flip over to observing platforms. Ships, floats, and gliders. We're not talking about everything here. We're just going to talk about 3 exemplary platforms. Ships, because they're the reference standard platform that we all use. You can look at this. There are phase lines here and the dash lines indicating gliders and ships. The kinds of scales they can resolve, everything in the upper left-hand side of that line, the things that they can resolve, everything to the lower right are things that they're too slow to resolve. And a traditional cruise is marked out by the red triangle, span of about a month. It can sample very short spatial and temporal scales, and it can make the whole ocean basin if it has to. If you combine lots of ships, you get the global hydrography program. You can sustain that over climate scales, so many, many years, but you only repeat a line every 5 years, 10 years, right? And it's got limited resolution, kind of a 100-kilometer resolution roughly. Add to that floats. Argo floats or floats in general, right? Provide a different perspective on things. Now you have the ability to be out there for a very long time, resolve scales on order of 100 kilometers, and do that at time scales of 10 days. Right? Pretty nice. It's a part of the face space that the ships have not been able to paint out. One float gives you a variety of different capabilities. And then if we think about gliders, that fills in this area over to the left, which lets you sample finer spatial scales, albeit in a much more limited area, right? So now you can do boundary currents over a long period of time. And we can put sensors on those platforms and deploy them in different ways to execute multi-platform process studies, kind of the purple box that we see there, by using a variety of these platforms. And what I'm going to do now is stop sharing, and Eric is going to take over.
Okay, yes, you guys can hear me, good. Okay, and here we go. Good, can you guys see that? Good. Not
Yes,
yet?
yes, Eric.
Okay, excellent.
We're
Oops,
seeing
let's try.
Got it.
There we go. Okay, so I'm going to try to make what Craig said a little bit more concrete. In 2018 to 2019, many of the people in the audience worked to make a multi-platform, as Craig was talking about, multi-scale observations of the Bay of Bengal, associated in particular with the monsoon, and in particular thinking about how fresh water, which comes into the northern Bay of Bengal, spreads out across the bay through boundary currents and through eddies to modify air-sea fluxes, and in particular plays a big role in the monsoon interseasonal oscillations, primarily because the fresh water makes a very thin layer near the surface, which makes the thermal mass of the ocean, effective thermal mass, small, and that makes the ocean timescales match the atmospheric timescales. That appears to be a big reason why there are monsoon interseasonal oscillations. The observation program on these large scales, hundreds of kilometers to 1,000 kilometers, was primarily based on enhancing existing observations, which in this region, which are pretty impressive. There's an array of Indian buoys here in green and joint US Indian buoys and also in green. These are Rama, those are Omni. There's a meteorological network with the blue stars that was enhanced, and in particular we added a buoy ship here that launched buoys, launched radio signs here. There were some extra moorings added, and all of that takes care of the interior of the basin. For the boundary current, which is also very important, there were 2 glider lines that have been continuously run off of Sri Lanka, and gliders go back and forth and they measure the transport of the East Indian coastal current. So this measures these larger scales. There was also, to get the smaller scales, there was a more focused experiment done on the edge of one of these eddies here. And I'll take a look at that. Focusing here on the 2019 experiment. This was focused on oceanic fronts, atmospheric convection, and mixing on both sides of the interface. And in particular, in the monsoon oscillations, there's an active phase of the monsoon in which a convective band and all the monsoon type things move northward across the Bay of Bengal. And this experiment was mostly focused on the transitions between active and break phases. In the active phase, of course, you have strong rainfall that modifies the air-sea fluxes. That modifies the ocean. In particular, you can get mixed layer deepening, for example, some freshening and heating and cooling, depending on the details of how that works. Now, this is a multi-scale experiment. We aim to go from scales of meters to tens of kilometers and somewhat larger than that in resolving daily timescales, both day-night and convection. Now, this, interestingly, was a ship-based experiment, but it was a multi-platform ship-based experiment. And this is a very modern way to do things, different than the traditional ship cruise. The ships are extremely capable platforms. You can look upward into the atmosphere using radar, downward using sonar. You can release balloons. You can make very high resolution profiles, really excellent profiles from a big ship like this. But that's not the only thing that ships can do and what they're used for today. The other thing you can do with them is put out arrays of additional buoys. This is what we did. These were not moored to the bottom, but drifting with big drag elements, had a profiling unit underneath, which gives you measurements. You can see the very high resolution measurements you can get from a platform like that. Ship also released a drone boat. Drone boats can do what a big ship can do, but not quite so well. And that could sail around and give us additional spatial resolution, and a glider. And the point is, with all these different measurements, you get not just a single measurement from a ship, but you get a whole region spanning these scales. And by combining these sort of measurements on the small scales with the type of measurements I showed you in the previous slide, on larger scales, we could span a very large range of scales and therefore a very large range of processes, which is what you need to do to study this problem. So go ahead, Craig.
So just to briefly summarize, wrap up the talk, I want to leave you with a few messages. So the most important, I think, is really that the important physical phenomena are really multi-scale, right? So any observational approaches that we undertake here have to be capable of capturing a broad range of temporal and spatial scales. As Eric was showing, there isn't a single platform that provides sufficient capability to do that. That was part of the reason for the exercise of plotting the range of 3 selected platforms in the phase space, right? You can see how they overlap and how they complement each other when you combine them. Eric and I have a soft spot for autonomous platforms. It's a large part of what we do for a living, but honestly, they provide access to a set of spatial and temporal scales that have been really difficult to get at in the past. In particular, its ability to maintain a persistent presence over a long period of time over a range of space, right? We've been able to do that with mooring for some time, but with limited spatial distribution. And the autonomous platforms allow us to fill in the gaps of that spatial sampling. And the other thing that Eric alluded to in his couple of slides there was that it really is regional leadership that makes a difference for these long-term observing efforts. But it's absolutely critical that the leadership for those efforts rests within the region. It's important for the science, it's important for the operations, it's important to be able to sustain it, right, and to do that efficiently. So that makes this effort that Monty, that you and your colleagues are undertaking absolutely critical. Thank you.
Thank you, Craig and Eric. I think we have time for a question, if there is any from the audience. Please feel free to ask questions. We have time for at least one question. If not, we can have a discussion later. Okay, thank you very much, Eric and Craig, and we'll look forward to further discussions later.